Last day of the workshop. The first lecture is going to be given by Professor Orlitsky on an estimation of large alphabets.
Okay.
Thank you.
Thank you very much. I would also like to thank the organizers, especially for this one, for inviting me. Yes. Better? Yep. Okay. We're going to talk about probability estimation of a large alphabet. Can you see? No. Maybe we can turn lights off down a little bit. Like, you think something like that? No. Oh, that's my phone. All right. Maybe in the back. Okay, perfect. Okay. And this is joint work with a number of my current and former students, and in particular, Prasad Santanan, Krishna Viswanathan, and Junan Jan. Okay, so we're going to talk about 4 problems: distribution modeling, classification, probability estimation, and compression. And we'll describe all of them from a unified viewpoint, which we call patterns, which we'll clearly describe in great detail. Okay, and because these are very basic problems, then a lot of famous people worked on them, and even some flora and fauna got involved, and we'll cover all of those. And as you can see here, it's actually a Cambridge story, so I'm actually very happy to give this talk here, because a lot of the people involved were very close to here, including actually the person that this institute is named after. But because this is an overview talk, we won't get into that detail, so we won't see how Newton comes in. Okay, so so let's start. So the only problem is that unlike all the previous talks in this workshop, this is going to be a somewhat bad talk. The reason is that if in a good talk, you take 2 things that are different and you make them look the same, and show that they're really the same. You take things that look complex and you show that they're really simple. You take things that are applied and you build a theory around them, like things that have been done here. And you take things that are boring and show that they're really interesting. In this talk, we'll take things that are obviously the same. We'll try to argue that they're different. Take things that are simple and make them complex. Take things that are theoretical and try to convince you that are applied, and take things that are interesting and talk about them for so long that they'll become boring.
It's also a blackboard talk.
That's right, it's also a blackboard talk, that's right. And in addition, there are also other minor things, like there are 4 topics that we'll discuss, so clearly we won't have time to discuss any of them in depth, and why we're wasting so much time. So anyway, okay, so let's start. Okay. So someone who lived not too far from here told us that a rose by any other name should smell the same. And in science, which is equally beautiful, if we conduct research in any language, we should get the same results. Okay, so let's test this hypothesis and try to find the distribution of swine flu cases in different countries. And since we're talking about language, maybe we should be a little more careful. Okay, so we're trying to say, for example, that maybe 20% of the swine flu cases are in England, 30% in France, and so on. Okay. So one thing that we can do is we could ask, for example, Venkat to do the research, and what he'll do is he'll read the newspaper, he'll see that there's a case in Mexico, a place in the USA, a case in Mexico again, Spain, and another case in Mexico, okay? So he should get the same results that, say, Francois would get if he conducted the research, and he would see that the first case is Mexique, and then États-Unis, Mexique, Espagne, and Mexique. So they should get the same results. What do they mean by that? We mean that the probability that Venkat is going to give the USA is the same as the probability that Francois should give the États-Unis. Okay? They should get the same answer. Okay? And this should hold not only if you conduct the research in English or French, but also if you conduct it in the universal language of mathematics. And if you did that, then what you do is the first country that you see, you'll just call it number 1. The second country you see, you call it number 2, and then number 1 again, and then number 3, that's a third country, and then country number 1. Okay, so this is what we call the pattern of the sequence. Okay? Okay, the first symbol that you see you call 1, the second symbol you call 2, and then you keep the numbers, you keep using those same numbers. Okay. So again, the probability that that the mathematician is going to give number 2 should be the same as the probability that Venkat gave the USA, right? That's what we would expect. Okay. And if you want to do something a little maybe more lucrative, we can look at horse race. So we want to find the probability of horses winning. So again, we look at some experiments or some results, and maybe we see Barbaro won and Seabiscuit, Barbaro and Barbaro. Then if we looked at the pattern, then what is the pattern here going to be? Barbaro is number 1, and then Seabiscuit is number 2, and then number 1 again, and number 1. Right? So this is the pattern of the sequence. And once again, we would expect the probability of Barbaro to be the same as the probability of 1, clearly. Okay? So we have two things that are the same, and what we want to do first is convince ourselves that they're really different, and if we manage to convince ourselves, then maybe even better. Okay? That's the goal. Okay, so just to make sure, because patterns are essential to this talk, just to make sure we all know what they are. So what they do is they replace each symbol by its order of appearance. Okay, and so for example, if we get this sequence ABBA, what is the pattern? 1, 2, 2, 1. If we take bananas, what is this? It's a little more complicated. 1, 2, 3, 2. Okay, and now reverse patterns. An English word whose pattern is 1, 2, 1.
I am I.
I am I. Okay, that's
is a phrase.
right. That's in words. But mom, that's not the slide I expected. Let me have another slide. Okay, let's actually in one. Oh, sorry. Okay, I think I have another slide here. Yeah, I modified the slide again here. Okay, so 1, 2, 1. We have this, or we have red, blue, red, or we have Francois. We cut Francois. Okay, and 1, 2, 4. 1 to 4, there won't be any, right? Because the next, after 2, we expect to see 3, okay? So what do patterns do? They capture the structure of and frequency of the symbols that we see, but they ignore the actual values, which normally we wouldn't care about, right? I mean, it's, okay. Right. Okay, so let's describe the first, we talked about what patterns are. Let's describe the first two, and we saw how these came in. Let's talk about distribution modeling and probability estimation. So these are two related problems. So in probability estimation, we want to associate probabilities with the outcomes. So for example, we want to say the probability of Spain, the fraction of cases that exist in Spain is 20%, in Mexico 50%, in the USA 30%. Okay? Or the probability the Seabiscuit will win is a quarter, probability Barbaro wins is 3/4. Okay? When we talk about distribution modeling, what we want to do is we want to disassociate the probabilities from the outcome. So we want to just estimate the probability multiset. So for example, instead of saying the probability of Spain is 0.2 and so on, we just said that the set of probabilities is 0.5, 0.3, and 0.2. We just ignore the association, just look at the multiset of probabilities. Okay. And likewise here, we'll just say 3/4 and 1/4. And because we're just looking at the multiset, we'll also always sort them. It doesn't matter, we just sort them, always decreasing. Okay. So these are the two problems, and we'll start with distribution modeling, the second problem. Okay. All right. So the first question to ask about distribution modeling is, why do we care? Why should I care about just the collection of probabilities without the association? If I'm betting on a horse, I want to know which horse is going to win. If I'm buying a stock, I want to know which stock is going to go up. Okay? So there are many reasons. One of them is lots of people are looking at population estimation. So you want to know the size of your support set, how many different species there are, how many different people there are, and so on. And for example, it's being used in sensor networks where you want to know how many sensors are alive. Okay? So in that case, you only care about the size of the set. So if you have this collection, then you also know its size. Okay, that's one case. Or I gave this talk once, and someone came afterwards and said that he works for a company. They they design drugs, and the way they do it, they're not. We think they're very smart, but apparently they're not much smarter than we are. And what they do is they take a bunch of molecules that they know are relevant, and they mix them together, and then they check them. And if it works, great. If not, they mix them again, and they check them. And they want to know when they have exhausted maybe 90% of the stable molecules that they could get, the stable compounds. So again, they don't care about the probability that a specific compound will be derived, but just the set of probabilities. Then they can figure out when they've covered 90% or so. Okay. Or if you build if you build a cell phone system, you want to be able to cover maybe the demand 90% of the time or 99% of the time. You don't care about the probability that each person will call, you just care about the collection of probabilities. So there are many other reasons. And in general, whenever you care about the statistics, you don't care about the names. That's what you care about. Okay? So there are many reasons to just look at this collection of distributions. Okay? So to see how this problem works, let's start by, since this talk is somewhat about language, let's talk about motionese. So let's assume that, let's imagine that, that the UFO is landed. And the first message that we hear is at, pound, and so on, namely 60 ats and 40 pounds. And that's the first message, okay? And then let's analyze the motionese language, and we're going to assume independence. So we're going to, in this talk, although there are extensions, we're going to assume that things are independent. Every symbol is independent of the other, okay? And that's because we are sampling. Okay. So if we do that, we'll say how many symbols are in motionese? How many symbols do they use? 2, clearly. And what are the probabilities? Probabilities are 0.6 and 0.4. And remember that we don't care about the association, so we just said the set of probabilities is 0.6 and 0.4. It's very clear. Okay. So what method did we use? Okay, so we probably did just some guessing, but you could also argue that we did empirical frequency, just the ratio of the symbols in the experiment, or equivalently maximum likelihood. Okay. So what is maximum likelihood? I know everyone knows, but just because we'll use it later on, let's repeat. So we're observing the sequence X, and we are looking for the distribution that will maximize the probability of X. Okay? So in this case, this was our sequence, 60 ats and 40 pounds. We call P of at P, P of pound 1 minus P. So the probability of the sequence is P to the 60 times 1 minus P to the 40. And then you differentiate, you equate to 0, and you get at the highest, the P that will maximize the probability is 0.6. Therefore, that's the probability of at, and the probability of pound is 1 minus that. And again, since we don't care about the association, we said the set of probabilities are 0.6 and 0.4. Very natural and very accurate in this case. Okay. And you notice that maximum likelihood will always agree with empirical frequency. So, for example, if these were all the observations, then it will give us 20%, 50%, and 30%, which will just sort like that. Okay. So maximum likelihood works very well in cases like this. Yes.
Why haven't you checked that there might have been a third symbol that occurred with some probability, but you saw it 0 times?
Yeah, that's a very, very good question. That's an excellent question. We'll come back to it in the next slide. But here we have a particular methodology, right? The methodology is that we're trying to look for the distribution and maximize the probability of the sequence. If you add any other symbol that does not appear, that will decrease the probability of the sequence. So if your methodology is maximum likelihood, you will never get new symbols. That is the essence here, and will clearly.
A priorized lab, I mean,
that's right. So you can
don't think at all.
Perfect. You can make all kinds of assumptions about a prior and so on, which will give you other symbols. But we're trying to do things without priors. But you could. That will be an alternative approach. But we don't want to make any assumptions about priors. Like, what prior would you take if you had a language that you didn't hear anything about? Okay. So it works well for small alphabets, like here, when we had alphabet of size 2 or 3 and the number of samples was 100, but it will work poorly for large alphabets if the number of samples was small compared to the alphabet size, the number of symbols that we see, and that's what we're going to observe in the next slide. So instead of motionese, let's modify the language a little bit and talk about this language. Okay? And let's assume we go to China, and we observe some symbols, and maybe these are the symbols we observe. Okay, any? That's very good, David, because apparently this is what it means. So we saw. I'm good. We had at least one person, understand this stuff. Okay, so we have. 100 symbols, and clearly all distinct because the alphabet is so large. And we're going to assume IID. Okay? So if we did maximum likelihood on the sequence like we did before, then what is the alphabet size that we would assume? 100. It will agree with empirical frequency, so it's 100, and the probability of each symbol is going to be 1%. Okay? Clearly, right? And this is a very poor model, and because it doesn't agree with our intuition. What's a better model? The better model would say that it comes from a large alphabet, maybe an infinite alphabet. So if that's the case, then we expect to see everything different. Okay? But this is not encapsulated by maximum likelihood. Okay? So instead, let's do a thought experiment and say we don't care about the probability of each element, we just care about the collection of elements. So so the values don't matter, and we may as well just consider the pattern. It's called 1, 2, 3, 4, 5 instead of whatever the symbols that I can pronounce. Okay? So instead of doing maximum likelihood on the sequence, we got to do maximum likelihood on the pattern. Okay? So this is what we said at the beginning should obviously be the same, because we're just replacing these names by 1, 2, 3, and so on. Okay, but let's see if it is. Okay, so what is the pattern of this sequence? All of them, trust me, are different. What is the pattern? 1, 2, up to 100. Okay, and all that this pattern says, when you see this pattern, all it says is that you have 100 samples and all of them were different. That's what it says. This is exactly what it says. Okay, what is the maximum likelihood? Which distribution will maximize the probability that this will be? We took 100 samples. This is the pattern. Which distribution will maximize the probability that that's the pattern we see?
There are an infinite number of symbols.
Exactly. It's exactly what we wanted. It's exactly a large distribution over possibly infinitely many symbols. Okay. So we see that the pattern, at least in the case of very large alphabet, it works very well. Okay. And we don't need any prior assumptions. Okay. So the question is, okay, but this is a very trivial example where all of them are different. What happens when the alphabet size is not infinite? It's smaller. Will the patterns work well there too? Okay. So instead of looking at the very largest alphabet, let's look at a very smallest alphabet. So we see that they're not obviously the same, and we see that they're different. And the question is and we see it's better for a very large alphabet. And the question is, number one, why? And number two, what happens to smaller alphabets? Will it still work better? Okay. All right. So before we do that, let's see why actually it was different. Why the results we got were different, where initially maybe we would have expected them to be the same. So let's compare sequences to patterns. Okay. So we're assuming that the sequence is generated independently and identically distributed. And again, this is only because we're doing sampling. So we're sampling from a distribution, so it's IID. But if you don't want to assume IID, there are extensions of this work. We just won't discuss them here. Okay. So it will induce a probability on the pattern. Okay, this sequence, which is generated IID, will induce a probability on the pattern, and the question what it is. So let's look at an example. So let's assume that the alphabet consists of 3 letters, A, B, C, and for simplicity, let's assume that the probabilities are the same. It's uniform, just so we can calculate things. Okay. So if we have one sample, what will be the pattern that we'll observe? Clearly, 1. Right? And what will the probability of this pattern be? If we take one sample, with probability 1, we'll get that pattern. Let's say we take 2 samples. Now we have more patterns possible. Okay, what are there? Could be 1, 1 or 1, 2. What is the probability of 1, 1? That's the probability that we either get AA or BB or CC. Those are exactly the cases we give us 1, 1. Okay. What is the probability that we see that? It's just 3 times 1/9, which is 1/3. Okay. So what's the probability? And that's the same as saying the probability that the second was equal to the first, which in this case it's again 1/3. Okay, okay. What is the probability of 1, 2? So we know already it's 1 minus this, so it's 2/3. But if we wanted to do it directly, it's the probability that we get either any of those sequences, right, A, B, and so on, or in other words, which is 2/3, as we expect. In other words, it's the probability that the second will not equal the first, which in this case, again, we can easily see is 2/3. So you see, the pattern actually tells you what happened. You just ignore the values. Okay. All right. So what we observe is the patterns are not IID. The probability of 1, 1 is not the probability of 1 squared. 1/3 is not 1 squared. And so therefore we get a different math and different results. So what we thought might be the same is actually different. Okay. All right. So what is pattern maximum likelihood? So how do we perform the maximum likelihood? So we're given a pattern. For example, in Chinese, we got 1, 2, 3 up to 100. And we want to find the highest distribution that this pattern can get and the distribution that can achieve this value. Okay? And that's it. That's all we're doing. So instead of maximize the probability of the sequence, maximize the probability of the pattern. So the only thing we're doing. Okay? So if we have length 1, then the only pattern is 1. What is the highest probability that this pattern can get? Clearly it's 1. Right? And it's achieved by which distributions?
Excuse me.
Yes.
Again, so what is the pattern? You didn't give a definition of this pattern. I'm just what's length of pattern doesn't.
Okay, so you take a...
I'm lost.
No, it's very good because you're asking, because otherwise you'd be lost for the rest of the talk. So let's say,
That's because you don't know Chinese.
Right.
You're missing half the story there.
Almost Chinese, all we know. So you're taking a sample of, let's say, length 10, And let's say
Yeah, no, the ABC, previously.
ABC. Okay, so if I give you, let's do it by example. If the sequence is ABB, the pattern is going to be 1, 2, 2, because A, I give it number 1, and B, I give it number 2, then I see B again, then I get 1, 2, 2.
No, return to the previous slide again. So
Sure, no problem.
you use you said 1 and 2. What is
Right.
1? What is pattern 1? Pattern 1 is ABC.
Oh, yeah, the pattern, the 1 could be either A, or B, or C.
Anything.
Anything.
It's the first symbol you see.
First new thing you see, you write 1. Next new thing you see, you write 2. Third new thing you see, you write 3.
1 may be confusing. Do you if you understand 1, 2, then maybe we'll go back to, do you understand that 1, 2 corresponds to exactly these? Because we assume that the alphabet now is ABC. We assume we know it, it's ABC. So if I tell you the pattern 1, 2, then we either got AB, A, C, B, one of these sequences. 6 possible sequences.
So those are all the patterns of length 1 or 2.
Apologies.
What you've got up there, you've done a calculation for all of the patterns.
That's right. So I'm asking, what is the probability that I will observe the pattern 1, 2? That's the probability that I'm looking at all possible sequences that would give me that pattern. That is the probability that I saw 1, 2.
So 1, 1 means probability of having repeat outcome.
Of any outcome.
Any repeat outcome.
No, 1 is any outcome.
No,
No,
1,
1.
Oh, 1, 1, yes, that's right. 1, 1 is any, that's correct, yes, exactly.
So you could consider a sum of probabilities. You
Exactly.
put a uniform distribution.
In this particular example, I'm putting the uniform distribution so we can get a simple.
Uniform prior and for
No prior, no prior. In this particular case, no. I'm just calculating the probability of an observation. In this particular case, I'm assuming that I have uniform distribution, but I could have calculated anything else. And then I calculate the probability that I see the pattern. The issue is this. What we believe is that if you only care about the set of probabilities, you don't care about the probability of A and B. All you should say, I saw 2 symbols and they were different. That's captured here. Or you should say, I saw 2 symbols and they were the same. That's captured by this pattern. So the pattern captures all the information you want to have. It's sufficient statistics. Okay? So that's why we look at the pattern. Is that okay? Right. Okay. So this one is by any distribution. Now, what is the highest probability that 1, 1 could get? The pattern 1, 1 could get? 1. And it's achieved by which distributions?
Focused on 1.
Any constant distributions, right? Any distribution that always gives the same symbol. Okay? And what is the highest probability that 1, 2 could get? Think Chinese? No, we think Chinese, right? If we think Chinese, if we one, and it's, sorry.
Infinite alphabet.
Right.
Large distribution.
Because we don't assume that the alphabet, we don't assume that because we saw 1, 2, that's the alphabet. Just like in maximum likelihood, we do not assume that. That came out from the calculation. Here, the calculation gives you that there are more alphabets. Okay. Right.
But if you need a probability distribution on the alphabet, then it can't be exactly 1.
Yeah, oh, no. Okay, okay.
It's as close to 1 as you like.
Yeah. All right. So actually, that's true. Actually, we allow for also continuous alphabets, but let's not talk about it. But you're right. Here, this supreme, at least we agree, is 1. But actually, the way we do it, it is 1. Okay.
So you introduce any prior distribution?
No prior.
No prior. You took prior, uniform prior.
No prior. I'm doing maximum likelihood. I'm not using any prior. Maximum likelihood assumes no prior.
You're specifying the parameterized model, right? So you're specifying, given the parameters, how do you...
Right. You
define
find a set of parameters that will maximize the
You want to
probability of the
maximize those
pattern.
parameters.
We definitely do not assume any prior. Okay. So if you look at 3, then 1, 1, 1 and 1, 2, 3 are the way we had before, and the first interesting pattern is 1, 1, 2. And the question is, what is this? So this is, remember, for large alphabets, it worked well. Here's an alphabet of size 2. Let's see if pattern works better than the sequence itself. If it works better for large alphabet, for such a small alphabet, we'll have a little more confidence. Okay. So this, because it's IID, the probability of 1, 1, 2 is the same as 1, 2, 1 and 1, 2, 2. All these will have the same probabilities. And and if we solve this, we'll solve all cases of length 3. Okay. So what's happening here? Imagine that we're flipping 3 coins and we see heads and tails. Just imagine. We're not assuming 3 coins, but just imagine. And we see heads and tails. So the pattern is 1, 1, 2. So sequence maximum likelihood will tell us that if we did that, then the probabilities are what? Whoa. Okay. Then the probabilities are 2/3 and 1/3. Okay. And what would pattern maximum likely tell you? That's what we'll do in this next slide. So
I have a question, but I mean, if you have an infinite alphabet, why wouldn't it be 0?
Exactly,
Yeah.
so it's not maximum.
we're looking at, if you have an infinite alphabet, this probability will be, you're right, will be 0. That's correct. If you had a uniform distribution of a very large alphabet, then this value will be 0. Okay, but we're trying to find the distribution that explains the observation. So we'll maximize over all distributions, infinite and finite. Okay, and that's what we're doing here. That's what we'll do in the next slide. Okay, so what we'll show is the highest probability that 112 can get is 1/4. It's no longer 1. Okay, so we show it's bigger than a quarter, and then we'll show less than a quarter. So bigger than a quarter is easy. Just take fair coins. Okay, half. What is the probability that 112 is the probability of heads, heads, tails, or tails, tails, tails? Heads, it's a sum of the probabilities, so it's a 1/8 plus 1/8, which is a quarter. So we see that it is a distribution that assigns to 112 the probability a quarter. The question is whether there is a distribution that will assign to it a probability higher than a quarter. Okay? And we show that there isn't, there is none. Okay? So the probability of 112, what is it? Is summation of all x in your distribution, and now x could range over any number of values, of the probability that x appears twice, and then something other than x appears. So it's summation of p squared x times 1 minus p of x. Okay? Now we just group them together like that, px times 1 minus p of x here, and then this is at most a quarter. P times 1 minus p is always at most a quarter, and a quarter comes out, and get it's at most a quarter. So what this shows us is that no matter which distribution you take, over any number of alphabets, any set of probabilities, the probability will never be more than a quarter. So the highest probability of, so the highest probability that 112 can get is a quarter, and it's achieved by coin flips, by uniform distribution over two values. Half. So sequence maximum likelihood tells us 2/3, 1/3, and pattern maximum likelihood tells us 1/2, 1/2. And the question is which is better in this very small case, okay? And again, if we can convince ourselves that pattern is better, then I think we'll be in some decent shape, okay? All right, so, okay, so one thing to observe is this. We don't care about the probability of heads and the probability of tails, just a set of probabilities, okay? And because we performed 3 experiments, we'll never get 1.5, 1.5. So the closest we can get to uniform is 2 and 1. Right? We can never get 1.5 heads and 1.5 tails. So we have to get some bias, and 2 and 1 is the closest to uniform. And in fact, so half is the closest to uniform, and any distribution like 2/3, 1/3 will increase the probability that one symbol will appear 3 times. Therefore, will decrease the probability that one appeared once and one appeared twice. So half actually is the most logical in this sense.
No, but there's a different information structure, right? In the pattern, you only see the pattern.
Correct.
When you develop the sequence maximum likelihood, you actually see the symbol.
Yeah, we
That's
believe.
how you come up with the different answers.
No, you're totally right. So the way we see it is when you look at the values, you're overfitting because you don't care about the values. Like if you saw one symbol heads or one symbol at, okay, then if you did sequence maximum, you said the probability of at is 1. But you're not trying to find the probability of at. You're just trying to find a set of probabilities. So the fact that you saw one symbol gives you no information, which is exactly captured by the pattern.
But in practice, Mexico, Spain is different from Spain, Mexico. So
Oh, no, not if you're trying to decide on the set of probabilities. If you're trying to find the probability of, but that will be the second part of the talk, because actually you can say that patterns are limited. What you're saying is, what you think is that patterns are limited to when you try to find a collection of probabilities. That's not true, because once you find Spain, Mexico, you're trying to say what is the next one. You say maybe Spain. But if you see the pattern 1, 1, 2, you ask yourself what is the next one. It's more likely to be 1 rather than 2. But you know that 1 corresponds to Spain, so the pattern actually conveys the information there too. That will be the second part of the talk. Yeah. Okay. Okay. So all the same, and so okay. So in this case, it's very easy to find the maximum likelihood of 1, 1, 2. And if you think it's too easy, try 1, 1, 2, 3. But not now. Okay? And just to give you an idea, we know how to calculate the probability to analytically determine the maximum likelihood probability of all patterns of length up to 7. Patterns of length 8, we already know them. And up to 7 is many papers. All right. Okay. Okay. So we have some theoretical results, but we'll talk about them tomorrow. Okay.
Never.
And we have some computational results, and we talk about them according to Francois when chicken grow teeth. But I want to show some experiments now. Okay. So we took a uniform distribution over 500 symbols, so it's shown here. And again, we don't have the values just because we just care about the set of probabilities. So it's 500, each of them 1 over 500. Okay? And we took 350 samples, and we saw 2 elements appearing 6 times, 3 elements appearing 4 times, and so on. There are 161 elements appearing once, and that means if you sum them up, that there are 242, almost half the elements did not appear. I'm sorry, 242 appeared, and more than half did not appear at all. Okay? So if you did maximum likelihood on the sequence, then you'll get the red thing. These are the things that appeared once, twice, and here you have more than 50% that actually you have not observed. So this is clearly a very bad estimation because number one, it misses the size of the support set, and number two, it misses the uniformity of the distribution. Okay. Now, if you do pattern maximum likelihood, you get the green line here. So number one, you see it's much more, and what does it do? It just, instead of maximize the probability of what you observe, it just says which distribution over any number of elements will maximize the probability. If you took 350 samples, then you see 2 appearing 6 times, 3 appearing 4 times, and so on. That's what you're doing, and that's what you should be doing. That's captured by the pattern. So if you maximize the probability of that pattern, then this is what you get. Now, of course, I told you we cannot do it for analytically for patterns of length more than 8, and so we're doing. So we're approximating the pattern. So, right. Okay. So you may think, okay, maybe we got lucky here. So here are 12 experiments. These are all the experiments we performed on exactly the same parameters, and they're ordered visually roughly from best to worst for the pattern. And you see that in all of them, the pattern is much better than the sequence itself. Some of them
you plot the result of your
right. So we
maximum likelihood of patterns.
On the patterns, yeah.
But I thought you said you can only compute that up to 7 or something.
Yeah.
So
Okay. But that's what I unsuccessfully tried to explain. We can only analytically, like if you give me the pattern, give an analytic expression up to length 7. 8 or above, we don't. We know for some, but we don't know for all. But we have an algorithm that tries to approximate the pattern. So it's a computer algorithm that you're given the pattern, and it will try to find the distribution that will maximize. There's no proof that it's the best. So in fact, the results
there's no proof that it's the best.
That's correct. So in fact, the result could be better than what we have here. Most likely, it's not the best. It's a heuristic algorithm. So
which
the
kind of pattern will give you the worst? What kind of pattern will give you worst fit?
So you see, these are random experiments, right? So you take 500 elements. It could be that you were so unlucky that all of you got the same thing. 350 samples, all the same thing appeared all the time. So it could happen.
Is the same distribution, different experiments?
That's right. The same distribution, which is the blue one, and the same number of samples, 350.
You're seeing a particular pattern each time.
Correct.
From which you are trying to find.
That's correct.
So, for example, in the last case.
Yeah. So here's the pattern. Okay. So yeah. So here you can see this. So here the pattern's written here. There's one element that appeared 5 times. Okay, and so on. So that's a little less than what you'd expect. So that's why the distribution is actually here is more uniform than you expect. When you do these experiments, you normally expect to have more repetitions that you see than you saw here. Okay, like here, you said 17 and appeared 3 times, 2 appeared.
And if you only have 500 letters, why does the distribution go above 500?
See, like if all of them were different, you took 350 symbols. If all of them were different, which is unlikely, but if all of them were different, tell you it's an infinite distribution. It doesn't know. Right? If you're unlucky and all took 500 symbols, 350 examples, all of them different, it will tell you an infinite distribution because you're unlucky. If all of them were the same, it will tell you it's a constant distribution.
If I think I understood the question, I think it was if you take a fixed sample, then you imagine permutations of that sample.
That's the same.
And you get different patterns, so you
Correct.
get different estimates.
No, that's a very good question. So if you go back here, if you see the description that I told you, actually I didn't even tell you the pattern. I told you 2 elements appear 6 times, 3 elements appear 4
So
times.
keep that invariant.
No, because it doesn't matter. Because it's IID, the pattern 112 has the same probability as 1 to 1. So I just don't give you the sequence. I say if 112, I tell you 1 element appeared twice, 1 element appeared once.
Because it only depends on the type.
It only depends on the type, correct. That's right. I didn't want to get another detail, but obviously I had to. Okay, so is that clear? So instead of telling you the pattern 1 or 2, I tell you 1 element appeared twice, 1 element appeared once, it's the same. Okay? Right, okay. So we call this the profile of the sequence instead of the pattern. So we're doing it still PML, still profile maximum. Okay, so this is for 350 samples. If instead you took 750 samples from the same distribution over 500 elements, okay? So now if you did sequence maximum likelihood, you'll see it will come closer to the actual distribution, but still miss a lot of elements, 100 and some, and still not give you uniform. If you did pattern maximum likelihood, you get almost the exact distribution. And if you repeated that experiment 12 times, then you get these. Many cases you can't even see the difference. And I showed you, in all of those, I showed you roughly the 6th I think in this case I showed you this one. But they're almost always the same.
Again, so you consider any combination. So yes, frequencies of something.
Correct.
You don't care which symbols.
Correct.
Correct. And so for each such a frequency, you find the optimal distribution.
Perfect. Yes. Exactly.
Yes. And so this is the only thing you're discussing.
The only thing I'm discussing in this part. Correct.
Yes.
That's the only.
They're not sum up to anything. They're not summing up to anything.
If you want, think the distribution sum to 1. We will find a collection of P1, P2, P3. If you want, think of them as summing to 1. I think that's a good. At this level, it's a good thing to think about. Yeah. Just because I said we allow for continuous parts, so but it will confuse you. Yes.
So you start with saying that I don't care about the identity of the outcome.
Right.
But now suppose I do this and I put back the identity of the outcome. Seemingly you're doing better, right?
No, because
here,
because this only gives you what is the highest probability, what is the second highest probability, and what is the third highest probability. It still doesn't give you whether you're right that you would think that 1-1 you'd associate. If you saw the pattern 1-1-2, you'd say 1-1 corresponds to the higher probability, 2 corresponds to the lower probability. But there's nothing that implies this because there could be randomness there too.
How do you represent the continuous part?
Let's not worry about the continuous part. And so, in these experiments, which are heuristic, we don't have a continuous part. Actually, we start with the distribution of size 20,000, and we'll let the algorithm run. So in this, and if there was a continuous part, it will give you a very, very small. Okay. Okay.
So what is the purpose exactly? I mean, no, I'm trying to understand.
To make things complicated.
To me, exactly. Yeah.
No, I mean,
thank you.
is it?
I think one purpose is to replace the red line here with a green line there. To me, that's a sufficient purpose. But another purpose is to talk about to get Hardy and Ramanujan and all these people involved, which at the pace we're going.
Yeah, perhaps I could just comment. I mean, one version of this problem that I think statisticians talk about is the problem: how many words did Shakespeare know? We have the sort of writings of Shakespeare, and we know that there are certain words he used 10 times, certain words he used 100 times. We should be able to estimate the number of words he knew, but used 0 times in his writing. Or another example is people fishing. A fisherman goes to a lake, he takes out fish one by one. Every time he sees a fish, he throws it back. And at the end of his day, he wants to know how many fish are in this lake. In other words, how many fish are there that I didn't see, but I can estimate their existence by the patterns that I did see. So there are interesting practical examples like that. Now you've done this model where each fish has an equal probability of being chosen, but then you change that they have different probabilities. You're trying to estimate not how many fish there are in total and what the probability is that the ith fish should be chosen when you next pay it. Now there are alternative models where you, for example, say that the number of ones that appear and the number of twos that appear have Poisson distributions, and then you can do exactly other maximum likelihood statistics. And those sort of things have been found sort of better ways of getting at these questions, like how many words did Shakespeare know.
That's right. We'll get to that. We'll get to many of these things that you mentioned. We do not want to make the assumption of a prior. We do not want to say it's Poisson. We don't know. We just want to see what can you do without making the assumption. And one thing I just want to make clear, we're not saying that it's uniform distribution. Like here, see, like we're not, like in this case we'll get because it comes from uniform distribution, but we're saying whatever the distribution is, we want to find it. Okay? In the previous case, you'd see more clearly that it wasn't uniform. Okay, right. Okay, so so these were synthetic experiments. Let's look at some more real experiments, and maybe one thing about what you said. Maybe I'm not so convinced about fish. Maybe because I'm not that recreational. But let's say you build a cache for your computer, and you want to know how big should the cache be so that very high probability you don't need to fetch pages from the memory. Okay. Then what you care about is exactly this. You care about the collection of probabilities that every page will be used. Okay, because then based on this collection of probabilities, you can determine what's the probability that a page will not be in the cache. Okay, so that's another. There are many cases. Whenever you care about statistics, you care about these values. Okay, right. Okay. So every 10 years in the US they conduct the census. In fact, this year it's coming up this year, and they're going to employ. I just read I want to say about 1 million people. I just read it, but it's a huge number of people just going from house to house, taking all these questions. And there's always a debate whether they should do it statistically. And so here are the results for last names from the 1919 census. So back then, Smith was the most popular name, 1% of the population. Johnson was the second one, and so on. And these are the cumulative probabilities, 1% and 1.8 and so on. They'll sum to 100 in the end. And these are just the order, the first, the second, and so on. Now, the list goes on, and we took it from the web, where the numbers that we get go up to 19,000 names, okay? Below that, all the probabilities are 0, so we can just not do anything with them. They just don't give us any more information. Okay. So we took these 19,000 names, and they cover 77% of the population, okay? So it's about, you can think of this 230 million, that's what they correspond to, okay? So this is what we worked on with, just this first top of the list, okay? So again, these names correspond to about 230 million. This is the distribution, if you plot that. You normalize it to 1. And this is what we worked with. Okay? And what we did was we took 15,000 samples from all of these, just 15,000, and we observed 10,000 names. So if you did empirical frequency, you'll get this red line. Again, you'll miss a lot. If you did maximum likelihood on the pattern, on the profile, then you'll get this. So it's a lot closer to this. And you can see we're not assuming it's uniform. Right? In fact, it's not uniform. All right. Okay, so now we're going back to your question. So one popular application of this is population estimation, and started here at Cambridge. Okay, so there was a naturalist, and maybe other people might know this story better than I do, called Courbet. He kept going to Malaya, it's now what we call Malaysia, and he tried to estimate how many different butterflies they had. But every time he went, he came back with more butterflies. So he got frustrated after a while. And he went to Fisher, who is, of course, one of the greatest statisticians of all times. And Fisher, of course, was the person who either invented or popularized maximum likelihood. So I'm sure that's the first thing that he thought of for like 1 second and realized it won't work for the reason we saw. And so they came up with exactly what we heard, like some assumptions about Poisson distribution with the gamma prior. And with that, you can get some calculations, okay? So then there was a lot of follow-up work. I mean, continues to these days. Good and Toulmin, and people count like the number of mutations of a gene, number of strains of a virus, and so on, and number of sensors, as I mentioned, and many others. Okay, but perhaps the most famous, as we just heard, is analysis of the works of work of Shakespeare. So Shakespeare wrote about 900,000 words, of which about 28,000 are distinct, and one should note that about half of them appear once. So his vocabulary was so large, you could just throw them away, those words, after we use them, disposable words. Okay. Okay. And so in 1976, Efron and Thisted wrote a paper called How Many Words Did Shakespeare Know? Okay, they estimated that if you wrote the same volume of work, another million, let's say, then there will be 11,000 new words in addition to those that were seen. Okay? And this paper went pretty much unnoticed until 10 years later, a poem was found, actually in Oxford, library, and it's called Shall I Die? And here it is, Shall I Die, Shall I Fly, and so on. And people suspected it was written by Shakespeare. I think it was written by a mathematician, because it's all about publication. As you can see in the second stanza, shall I send, shall I tend to ascend, and not rule my proceeding, you know, so. But this poem is 429 words, 9 of which are new. Okay, these are the, maybe the most interesting one is Bizots. People know what Bizots mean?
Besotted, right?
Besotted, right. Means?
Well, madly in love.
Okay, so it means that you make you're made dull or stupid either by love as Venkat thinks, or by being drunk. Right. So you can say that this talk you're besotted, if you want to be vague. So, right. So then they Thisted and Efron published another paper, and they analyzed this. You know, they said what happened if Shakespeare wrote 429 words, and they showed that they expected about 7 new, and this considered 7 close to 9. So the paper got a lot of publicity. Okay. But now, if you do the analysis that we said, and you get the distribution, you don't care about the words, but you can calculate the probability that you'll get. If you wrote another 429 words, what's the probability that you'll get how many will be new? If you do that, you get 6.98. So it's essentially the same. Okay, if anything, better, but let's call it the same. Okay? So, and this, of course, assumes nothing, no prior, no nothing, number one. Number two, once you have the distribution, you can calculate a lot of different things, like how many words will appear 2 times, 3 times, everything. The formula is specific for this calculation of how many different things will be there.
Yeah, excuse me, but why would you expect that the proportion of new words should be the same as the average? I mean,
okay, that's a very good question, and that's also an assumption that all these calculations do. It's a very good question. But all these calculations also do this. They say, on the average, if you wrote this, how much will be new?
Yeah, it's like Shakespeare writing it. Wait a second, I don't have enough new words. I mean, didn't we put...
No, I wouldn't say that. I wouldn't say that. The difference is that you assume that what Shakespeare wrote is typical to what he would have written, and then you say how many will be new. But that's common. I agree. That's a criticism. It's a criticism here, and it's a criticism here. I agree. It doesn't say, okay, if Shakespeare wrote this, maybe it's not exactly a random thing. Maybe it's not exactly ID. It doesn't say all of that. I totally agree, but it's a common. That's all the works that do this, all the work that he mentions makes this assumption. All right. Okay. So we talked about distribution modeling, okay, and we saw we saw 2 people coming in, and maybe we convinced ourselves the same is actually really different. Right? And what we want to talk about now is probability estimation. Okay. So now instead of just looking at a set of probabilities, we want to say the specific probability. Probability of Mexico is 0.5, probability of USA is 0.3, and so on. Okay, instead of points 3/4 and 1/4, we'll set Barbara wins probability 3/4 and Seabiscuit wins probability 1/4. And as we discussed a few minutes earlier, you can see that patterns you'd initially think you lost the connection between the value and the probability, but you really don't, because if you have Mexico, Spain, then the sequence is 1, 1, 2. You're going to give probability to 1, which you know corresponds to Mexico, and probability to 2, which you know corresponds to Spain. So actually, you did not lose the association, and that's why patterns can also work for this problem. Okay, so so to see what happens here, let's imagine that. So we don't have that much time. Like, I knew this talk was going to go to the edge, but it looks like it's going to go over the edge. So what should we do? Okay, so it's not as bad as it looks because
about 15 minutes.
Yeah, 15 minutes, and you realize we covered 1 out of 4 topics. But sorry? Okay. Oh, thank you. Okay. Okay. Good. Okay. And we'll finish con les dents or con les poules au rang. Right. Okay. So so you observe a sample of animals, and let's say this. Okay. And from this, you want to decide on the distribution of the animals you'll see. Okay. So so the simplest thing to do is, of course, empirical frequency. Okay. And there are 6 animals. Giraffes appeared once. We give 1/6, 2/6, and 3/6, 1/2. Okay. And is there a problem here? Good. Some people woke up. So we may not come back from this trip, right? And of course, what happened is that there were things that we did not expect that occurred, right? Okay. So this problem occupied the French. Obviously, still occupies them. They're here, but for a long time. About 200 years ago, they're concerned with the probability the sun will not rise. And why? Because they saw that the sun rose, but being very smart, they knew that this could happen also. So they had different estimators to come up with the probability that the sun will not rise. The one that survives till today is the one by Laplace. And he said you add 1 to each count, including to new. So if the sun rose n times, you pretend it rose n plus 1. If it rose 0 times, by definition, didn't rise. Then you pretend it didn't rise once, and you need to make it into a distribution. So you're n plus 2, probably is n plus 1 over n plus 2, and 1 over n plus 2. Yeah? Okay. So for our case, for the Safari, we just add 1 to each count, okay, and 1 new. And this is the new probability distribution. You see that we're giving new some probability, which is 1 over 10 in this case. Okay? And the question is, and the many you can add instead of 1, there are many variations. We won't get into those. And the question is, are they good? Okay? Right. So to do that, let's go back to the biology experiments, and let's try to find the distribution of DNA sequences. Okay? It's a very stupid question because it's not that there is one DNA sequence that is shared by half the people here. every DNA sequence is unique, so there's no distribution. You can't say that this DNA sequence is shared by 30%, 20%, so on. All unique. But that's what we hope to find from this experiment. Okay? So we take a large number of samples. Clearly, all will be different. So if we did Laplace estimate, then any observed sequence will appear once. We give it a count of 2, 1 plus 1. And unobserved or new will give a count of 1, 0 plus 1. So we have n of those and 1 of those. So when we normalize by 2n plus 1, and each observed sequence will get probably 2 over 2n plus 1. New will get probably 1 over 2n plus 1. I should mention this is just one way of extending Laplace, but other methods will not work better. Right. Okay. So is there a problem in this distribution? We're saying that the probability of any sequence you observe is 2 over 2n plus 1, and probability of new is 1 over 2n plus 1. But that's right. We're almost certain that we are certain it's going to be new, but according to this, it's almost certain it will going to be one of those that we observed. So it gives probability of new 1 over 2n plus 1. Observed will give 2n over 2n plus 1. So probability of new is roughly 0, and the probability of observed is n times this, which is roughly 1, and the opposite is more what we want to get. Okay, so this was a problem that Good and Turing encountered, and here is the story. So this was, of course, during World War II, and there was a small war going on in which there were about 3,600 vessels, Allied vessels that were sunk. So if you calculate, it's about 3 a day. So it's a big deal. And the culprits were the U-boats, of which there were about 1,000, the Germans built. And the communication with them was done via the Enigma machine and the Enigma cipher. And so there was a major effort going on at Bletchley Park to decipher this. And I'm sure people here know why Bletchley Park was chosen, as opposed to other locations. Because I guess it's on the line connecting Cambridge, train line connecting Cambridge and Oxford. So. Okay. And amongst the things they did was they built the first computer, but clearly it was not as fast as even this slow one. And so they also had 12,000 people working, and what many of them were doing was trying to use statistical clues to decipher things. Okay? And what helped them a lot was that they captured the German book of keys. So the Germans, being very precise, they didn't want to let the U-boat commanders choose their password. So they told them, here, you have a book. Don't choose your girlfriend's name, your wife's name, just choose from this book, and every day they had to choose. Now, they had managed to decrypt a few transmissions, so they had some previous decryption, and based on that, they were trying to find a distribution from which each commander will choose the password. So maybe from the beginning of the book, from the center, from the top of the page, and so on. Okay. So again, it's number of pages is very large compared to the number of samples, number of decryptions that they had. So it's the same problem that we're looking at. Okay. So what I could do is I could skip the Good Turing estimator if people want because of time constraints. But so Good and Turing came up with an estimator to describe the estimator. Beforehand, we needed a few animals. Now we need the whole Noah's Ark. But I'm going to skip the description in the interest of time, although it's interesting, of course, maybe more interesting than the talk itself. So anyways, they had a very surprising estimator, which is described here. So some estimators are that it's, they modify your estimate. They take Laplace, they start with Laplace, and then they modify it in an unexpected way. Like they look at how many animals appeared more than what you're looking at, and divide by how many animals appear the same number of times. It's not clear why you'd want to do that. Okay. So it's surprising and complex. It's complex, but it works well for infrequent elements, for things that appeared few times. It does not work well for things that appeared many times. So if something you've observed half the times, you don't want to use Good Turing for that. And so it's used in speech recognition and so on, and machine translation data mine, because suboptimal. Then people look at modification. There's empirical frequency for frequent elements, and then Good Turing for small elements. There are many modifications, and there are papers written like Good Turing frequency estimation without tiers and so on. Now, the formula, which I now regret not showing you, is actually very unintuitive. Okay. And so this actually is where what should have been simple becomes complex. And Good published the work after the war in 1953. It was declassified, and he wrote that the formula was suggested to him along with an intuitive demonstration by Turing. But he doesn't say what the explanation was. It does give some explanation, but it's not clear if it's the same. Okay? But this explanation, as well as some others, they're all just intuitive, why you might want to do this. Okay? But they're not rigorous. They don't say, if you do this, this is how far you'll be, or you'll converge, or anything like that. Okay? So rigorous explanation started in 2000. That's McAllister and Shapiri, and then that's our paper, and then there was some follow-up papers, Druk and Mansour, and this is Wagner, Kulkarni, and Viswanath. Okay. So, okay. So what is the plan? What we want to do is we want to come up with a measure for evaluating estimators, and we call it attenuation. Okay. So we need to come up with a measure saying this estimator is good, this estimator is bad. Call it attenuation. And what we'll do is we'll evaluate empirical frequency, Laplace, and good Turing, and then we'll see how Hardy and Ramanujan come in to give us an optimal estimator. I put it in quote because it's optimal based on this measure. Okay. So what is attenuation? So we have an underlying distribution P, which is clearly unknown. That's the problem. So we observe some sequence X, and what we hope, when we assign probability to the sequence, and what we hope is that, and we compare it to the actual probability of the sequence. And what we hope is that they should be close. P and Q should be close. But instead, in attenuation, what we care about is that Q is almost as high as P. So we don't want to underestimate. We don't mind overestimating, but we don't want to underestimate. Okay, that's what we care about. Okay, why do we only care about underestimation? We'll talk about that soon.
So you can always assign to be 1 then.
No, because you have to make Q has to be a probability distribution. P is a probability distribution. Q is a probability distribution. So they both have to be distributions.
For every sequence.
Right.
So I'm confused. How is this different from the earlier problem we talked about, the pattern distribution?
Okay. So in this, you care about the actual values. You care about X, the actual values that you see.
I see.
Right. But we're clearly using the same technique. Right. Okay. So formally, the attenuation. This is the actual distribution P. This is what probability we give. The ratio is by how much you underestimate. Okay, so for example, if this is 1 and we give probability half, then we underestimate by a factor of 2. Okay, so we're going to be super conservative. We're going to look at our worst attenuation of all possible distributions. Now here in this talk, it's IID. All IID distributions, and then we're going to look at all possible sequences. So we're saying we're counting our attenuation by the worst case possible. All distributions, all sequences. But this is distribution. This is our attenuation for sequence of length n for the whole vector. So we're going to take the nth what we see by how much we underestimate each symbol, okay? And then we'll let this value go to infinity, and that's what we define the attenuation. Okay? So what is it? It's the asymptotic per symbol worst case attenuation, the worst case over all possible values. Okay? And it's also the largest underestimation factor per symbol. All these 3 lines say the same thing. Okay? Just to emphasize. Now, even though these results define asymptotically, the definition is asymptotic, the result we'll get will hold for every n. So we'll say we'll get a bound for every given n. What is the attenuation? Okay. All right. So some observations is that in the worst case, we underestimate each symbol by this factor, and so we want low attenuation. We want to underestimate by a little bit. And P and Q are both probability distribution. Goes back to David's question. So there's a P and this is Q. Q has to be a distribution. And they integrate to 1, so for some value, we must underestimate. Okay? So for some value must be less than P, and so the attenuation is at least 1, and the hope is to get attenuation, which is 1. So if the attenuation is strictly bigger than 1, that means we underestimate each symbol by a factor bigger than 1, so we underestimate the whole sequence exponentially. If the attenuation is 1, that means we underestimate each symbol by a factor that goes to 1, and underestimate the whole sequence sub-exponentially. So that's the holy grail. We want to underestimate sub-exponentially as opposed to exponentially when we look at the whole sequence. And when you think about the probabilities will go down exponentially because of the IID, so we want to not be much slower than that. We want to have the same exponent as the actual distribution. Okay. So why do we care about underestimation? And not overestimation. So if the attenuation is 1, that means we do not underestimate, and that by itself is an important quantity. Right? There are many cases in which you don't want to underestimate. Okay? Then, because we have 2 distributions, if you don't underestimate, that means you do not also overestimate, because if you overestimate in one location, then you have to underestimate in another location. So that roughly means roughly means that you also do not overestimate. Okay, so just because of that, right?
So is Q based on patterns or on sequences?
Our estimate is based on the pattern, but just like we said, after you've seen the pattern, you can give values to things that you have seen. So we use the patterns. Yeah. Okay. Okay. And also, you can show that if you don't have underestimation, then you have diminishing KL divergence. That's because what is the KL divergence? It's just the expected value of P over Q. The KL divergence is the measure people like to use. Is the expected value of P over Q. But in our case, P over Q goes to 1. Log P over Q will go to 0. And this, in our case, it's in the worst case, this is just on the average. Okay, right. So so it will give you diminishing KL divergence, and because of that, you can show it will give you diminishing variational distance and so on. So, okay, so attenuation is much stronger than it appears. Okay, it implies all these things, and it's simple, and most importantly, we can actually show that you can get attenuation, which is 1. So, so let's evaluate some things that we've seen. So empirical frequency, we know gives to nu probability 0. Okay, that's what we saw. But nu will in general have some probability. So when you look at the ratio of P over Q, you'll get infinite. Okay, so the attenuation of frequency is clearly infinite. So that's not interesting. For Laplace, you can consider, for example, DNA sequence of Chinese, and you get everything is nu, nu, nu. Now, the probability, if you remember, that Laplace will give nu is 1 over 2n minus 1. So when you take this, when you look at the probability of the whole sequence, you take this product will go to 1 over infinity, essentially. But the highest probability that Chinese could give a sequence is 1, 1, 1, 1, 1. So that probability is 1, right? So the ratio is, again, take the ratio, take the nth root, again, goes to infinity. So Laplace also has an infinite attenuation. Now, good in Turing, we didn't describe them, so I cannot get into the details. I considered 3 versions. As I mentioned, there are many versions. The simplest one gives an attenuation which is at most 2, so at least it's not infinite, but it's at least 1.39, okay? And then the others gives 1.2 and 1.5, okay? At least 1.8. These we cannot analyze, but we can just argue that that will be the case, okay? So what that means is that for the whole sequence, you attenuate by an exponential factor. Look at the whole sequence. Okay. All right. So how do you get diminishing attenuations? You use results by Hardy-Ramanujan to show that the attenuation is at most. You can construct an estimator whose attenuation is at most 2 to the square root of n. So instead, not 2 to the length of the sequence, but 2 to the square root of the length of the sequence. So this is attenuation for the whole sequence. So when you look per symbol, it's 2 to the 1 over square root of n. Take the nth root of this. So this will go to 1, and we know exactly how it goes to 1. So for example, if you're looking at a sequence of length 100, there is some small constant involved, but ignoring that, if you're looking at a sequence of length 100, then you're looking here at the 10th root of 2. So that's a bound on your attenuation.
What's the complexity of computing Q?
Okay, we'll get to that in 1 second. Okay. And so this particular attenuation requires 2 to the square root of n operations per symbol. Okay. But we have an efficient algorithm whose complexity is slightly higher than this, is 2 to the n to the 2/3. Okay, instead of this, it's still sub-exponential, so still when you take the nth root, it will go to 1. A little slower, but still go to 1. And this can be done, sorry. This can be done sequentially, and it can be done with a constant number of operations per symbol. So every symbol you see is a constant number of operations, okay, and a small number. Okay, okay, so okay, so what does it have to do with Hardy and Ramanujan's? So they've worked on partitions, and partitions are positive integers that add to a given integer n. And Pn is the number of such partitions. So for example, 1, you can just write it as itself, so its partition number is 1. 2 you can write as 2 or 1 plus 1, partition number 2. 3 you can write in 3 ways, and 4 you can write in 5 different ways. Okay, so it's partition number 5, and the question is, what is the partition number of n? That's a work that the Greeks started thinking about. Euler developed generating functions partly to look at this problem, and so on. And of course, Hardy and Ramanujan have very well known for working on this. So they derived the formula for the partition number, which showed that it's roughly 2 to the square root of n. Okay, and interestingly enough, they thought it was an approximate formula, and then apparently this is actually little was said. that they thought this formula was approximate, but there was a retired British major who calculated the partition number up to like 200.
He's a very good mathematician.
Yeah, and a very good mathematician, right? And designed actually like a precursor of the Rubik's Cube and so on. So you can see square root of 200 is maybe, I don't know, 13, 14, something like that, 14. And so if you take 2 to the 14 is 16,000. So you can see if you're a good mathematician, if you're retired, and if you have no internet, you can get there. And he found that it was actually the same as the formula. So they went back and they analyzed it, and then they realized the formula was actually precise, and some people call it like one of the jewels of 20th century analysis. There are plays about this and so on. Right. So
Actually, Harvey wanted to stop. It was Ramanujan who said, no, I'm sure we can do better.
I see.
This is one of the in one of the unpublished letters.
I see. So they after they do better, meaning
I mean, Hardy thought the paper was finished, and then Ramanujan insisted that.
I see. Okay.
I'm sure we can do better.
Thanks. Okay. Yeah. Thank you. Okay. So So what do probabilities have to do with partitions? Okay. So we want to learn the probability of each scene elements, and let's say of nu. So if we saw SAM, I, M, I, and so on, then after that we want to predict SAM, I, and M, and nu. We want to say what is the probability of SAM, what is the probability of I, what is the probability of M, what's the probability of what you'll see is nu. Okay. So if we look at the pattern 1, 2, 3, 2, 3 here, then we want to find the probability of 1, 2, 3, and 4. 4 would correspond to nu. Okay, so 1 would say this is where you see the connection between the patterns will give you the probability of the actual symbol, because the probability of 1 is going to be the probability of SAM. Probability of 2 is going to be the probability of I, and so on. So you can use it for that purpose. Okay, so this is what we want to do. So this is how patterns are used. Okay, and how fast can we learn? That's what we're interested in. Depends on the number of parameters of this distribution. Okay, so and furthermore, the number of parameters is determined by the data. So if I tell you, for example, if I told you that I have an ID distribution over coin flips, so just one parameter, what is the probability of heads? Okay, then you look at the data, okay, and you ask yourself, how many values can I get? The number of values that you can get is n, because you just ask how many times you've seen heads. That's sufficient statistics. Okay, so the number of values will be maybe n plus 1, from 0 heads to n heads, n plus 1. So this determines, of course we don't see the proof, but essentially this determines the speed at which you can learn. So if you look at ID distribution, so actually the pattern is sufficient statistic, but even the pattern itself doesn't matter. We've actually covered this, because probability of 1, 1, 2 is the same as probability of 1 to 1, same as probability of 1 to 2. So what we care about, only how many values appeared how many times. And as I said, we've already talked about it because of all the questions we got. So in this case, we care that, there's one element that appeared twice and one element that appeared once. Or if we had take n samples, maybe we'll care that 2 elements appeared 3 times, 4 elements appeared once. That's only information we have. Yeah, we'll just finish this. There'll be a test at the end of this part and also. Okay. So what this means is that we write 10 as 2 elements 3 times 3 plus 3, and then plus 1 appearing 4 times. Okay. So what we see is that this thing that we care about, which is we call the profile, corresponds to a partition. And the question is how many partitions there are that will determine how fast we can learn the distribution. So the number of possible outcomes that we can get is the partition number, which, as we saw, is 2 to the square root of n. So that's the 2 to the square root of n that we have in the calculation. There's a little bit of work we need to do, but that's the connection. All right. Okay, so a test. Okay. So suppose we've seen A. The same symbol appeared many times. So the sun rose. We want to predict, so we're going to say what is the probability of A, and what's the probability of nu. Okay. So sun rose a million times. What we say is the probability that it will not rise. And I'm not asking for a precise value, just is it close to 0, to half, to 1. So what is the probability that the sun will not rise? Close to 0. Okay, the estimator agrees with you. It actually says 1 over n. We don't care about that particular value. Okay. Now suppose we take again knowledge of experiment. We see AB. So we see 2 values, each appearing half the times. Okay. If you tell me the probability of nu, then by symmetry we'll determine this. Okay, so I flip the coin, half the time get heads, half the time tails. What's the probability will fall on its side? Close to 0. Very good. Okay. Now we go to China. Every symbol is different, or DNA. What's the probability of nu? 1. Very good. So at this point, I've wasted a lot of your time for something very obvious, right? But you also notice that this something is very obvious, maybe because all these numbers are either 0 or 1, and maybe we're very good with zeros and 1. We're information theorists. Right. Okay. So let's look at something a little different. And I suspect that often, or maybe always, when the answer is not 0 or 1, we'll fail. Okay. So I shouldn't say that, but often when it's not 0 or 1. So here's an experiment which, as opposed to this case, where we had 2 elements each appearing half the time, here we have half. If we took 1,000 samples, we see 500 different elements, each appearing twice. Okay? So for example, A, B, B, C, C, and so on. And I wrote them in this order, the IID, so the order doesn't matter. I just wrote it like that so it's clear what's happening. Okay? So what would you say is the probability of mu? That will determine everything by symmetry.
Time is odd or even.
Okay, let's give me 2 answers.
Either one or 0.
So what would your answers be?
So yes, each odd time you get 1, and each
Okay, so you say once it's 1 and the other time is 0.
Yeah.
1/2.
Okay, so 1/2, right? Both of you agree. So we got 2 1/2, and that was actually our estimate. Okay, so let's see what the estimator says. So the estimator, like you said, it's actually surprising that you do something different after even or odd, because it's assumed IID, so it should not matter. But let's ignore that. After an even number of times, after an even number of times it says a quarter. After an odd number of times it says 0. And again, I don't care about the even and odd because IID is not important. What I care about is that both cases it's less than a quarter. So it thinks it's somewhere between 0 and a quarter. So it doesn't think it's a half. Okay? So it's somewhere between 0 and a quarter. And if you did 1/2, you will get your attenuation will actually be positive. Okay. All right. So why? And by the way, why would we think 1/2? One possible explanation for why we might have thought 1/2, for those who don't see it, is because we did 1,000 experiments, and half the time we got new, half the time we didn't get new. So roughly every other time we get new. So that's a reasonable assumption. Okay. So why does the estimator think it's less than 1/2? So one possible explanation, we don't know exactly how it works, but one possible explanation is this. It says that if you take 1,000 samples and you see 500 different elements each appearing twice, you can ask yourself, what is the most likely underlying alphabet? If you did that calculation, which you can do, you'll see that it's roughly most likely comes from a distribution of 620 elements. If you did the population estimation, 620 different elements, each with a uniform distribution. Okay? And if that's the case, then you have 620 elements, of which you've seen 500. So the probability of nu is roughly 120 divided by 500, or roughly 0.2. Okay? So, but this is not the explanation that the estimator does what he does. This is one possible explanation. So with that, we've covered half of the talk, and maybe I convinced you that and we saw how some more people. Maybe I convinced you also that simple is actually a little more complex. Okay, and the main thing that I want to say is that we really, when you think about it, you really should be thinking of the patterns, because the values that you see are meaningless. So you should not give them names. You could say, I saw here's the first element, here's the second element, here's the first element again. You should do your math on that. When you do your math on that, you get patterns naturally. That's exactly what you get. Yeah.
Okay, let's thank the speaker. Unfortunately, given the time, we cannot really have questions here. So let's have questions privately, and the next talk will have to be at 11.